Good morning, grade 11. This is Mrs. Pascal. Today's lesson is about polynomials, chapter 5, section 5.3. The objective of this section is to solve polynomial equations by factoring or by using the discriminant. Number 1, solving a polynomial equation of degree 3. First, we need to rearrange the equation in order to obtain equal to 0. So it's 2x cubed minus 5x squared minus 3x equal to 0. Factoring it, we need to take the least variable with the least power. So we take x in common. So we get 2x squared minus 5x minus 3 is equal to 0. Taking each factor is equal to 0, x is equal to 0, or 2x squared minus 5x minus 3 is equal to 0. This is a second degree equation. It can be solved by using the sum and product way of factorization, or simply by using delta, the discriminant. So delta is 49, it's positive, so we have two real roots. X1 is equal minus half and x2 is equal to 3. So the final solutions for the equation of degree 3 are 0, negative half, and 3. The second polynomial equation is of degree 4. It's 3x4 minus 6x cubed plus 12x squared. So we can take the variable with the least power is of degree 2. So we take x squared in common. We get 3x squared minus 6x plus 12 equal to 0. Again, taking each factor equal to 0, x squared is 0, or 3x squared minus 6x plus 12 is equal to 0. So solving the first equation, we get x equal to 0. Solving the second equation using the discriminant delta, we get minus 108. So this equation admits two imaginary roots, x1 and x2. First, let's calculate to find x1. x1 is equal to 6 minus 108 I squared over 6. Reducing this fraction, we get 6 minus 6i radical 3 over 6, so 1 minus I radical 3. Once we get the first root from the two imaginary roots, the second one is the conjugate of the first one, so we can directly write x squared is equal 1 plus I radical 3. Or even if you apply the rule of the second root, we will get 1 plus I radical 3. So the zeros of this equation, or the roots of this equation, are two imaginary numbers and one real number. 0, 1 plus I radical 3, or 1 minus I radical 3. Now we have a polynomial equation of degree 4 in the form of x4 minus 3x squared minus 4 equal to 0. As you notice, in this equation, we don't have an odd power. So this type of equation is called the bi-squared equation. To solve a bi-squared equation, we need to transform it or to rewrite it in the form of a quadratic equation. So we need to take a supposition a equal to x squared. Replacing a in terms of x squared in the equation, we get a squared minus 3a minus 4 is equal to 0. It's a second degree equation or a quadratic equation with evident roots, since we can have 1 minus 3 minus 4 is equal to 0. So the sum of the first and the last coefficient with the difference of the second coefficient is equal to 0. So we have evident root x1 or a1 is equal to negative 1, a2 is equal to 4. Solving now for x. So replacing a by x, it's x squared equal -1 or x squared equal to 4. Solving this equation, x squared equal to -1 admits imaginary roots. So replacing -1 by I squared, we get x equal plus or minus I. For the equation x squared is equal to 4, we get x equal plus or minus 2. So this equation, this bi-squared equation, admits 4 zeros, 2 real roots with 2 imaginary roots, plus or minus I, plus or minus 2. In number 4, it's also a bi-squared equation since it's a polynomial equation of degree 4 with no odd power. So taking the supposition a equal to x squared, we get the equation a squared minus 10a plus 9 is equal to 0. Adding directly the coefficients of this equation, we get 0. So we can directly find the evident roots of this equation. A1 is equal to 1 and A2 is equal to 9. Solving for x, it's x squared equal 1 and x squared equal to 9. So x equal plus or minus 1 and x equal plus or minus 3. So this fourth degree polynomial admits 4 real roots plus or minus 1 plus or minus 3. Thank you.